In this lesson, we're going to introduce circle proofs. So the first thing before we get started on actually proving triangles inside of circles, we have to know some different theorems that we can use. So in this video, we're only going to focus on theorems about arcs and angles. So if you look at this first picture here, if you have congruent central angles, well, then that means that the arcs have to be congruent. Or vice versa. If you have congruent arcs, well, then the central angles have to be congruent. So it makes perfect sense. So really, if you wanted to shorten this, we can say in a circle, if we have congruent central angles, that's going to imply congruent arcs. But you can also go the other way. So I can also say in a circle, congruent arcs also implies congruent central angles. So as long as you have one, well, then the other has to be true. One thing that is really important, though, is that you mention the type of angle you're talking about. Because if you don't have the same type of angle, well, this isn't going to be true, because if you think about your formulas, you'd be using a different formula. So it has to be the same type of angle that's true. So if you look at the next scenario, if we have congruent central angles, well, then that also means that these chords that connect from A to B and then from C to D have to be congruent. So we know that if the central angles are congruent, it's really the arcs that are congruent as well as these chords. So the shortcut for this is to say in a circle, congruent central angles implies congruent chords. And again, you can do the opposite. You can mention this the opposite direction. So meaning if I have the congruent chords, well, then that also implies that the central angles are congruent. So I can go both directions. So that's why I'm putting the double arrow on. The next theorem here is saying that if we have congruent arcs, well, then we also have to have congruent chords. So if you think about what this was saying in this picture, these first two, if you had congruent central angles, then the chords were congruent as well as the arcs. The next theorem is basically saying, well, if we don't worry about the angles and we're just looking at the chords, well, if you have congruent chords, then the arcs that those chords cut into have to be congruent, and vice versa, meaning if I have the congruent arcs, so if these two arcs are congruent, well, then the chords that cut into those have to be congruent. So as long as you have one, you'll have the other. So for this one, I'll say in a circle, if I have congruent arcs, that's going to imply congruent chords. But remember, we can write this in the other direction. So I can also put I can put the arrow going the other way. The next idea here is if you have congruent inscribed angles that have congruent inscribed angles are going to have congruent arcs. So let's sketch a picture of that since we don't have it. So basically, if you have a situation, let's get a couple inscribed angles drawn here. So if I look at angle 1 and 2, and those cut into two arcs that are congruent. So if these two arcs are congruent, they don't look congruent in my picture, but if they were congruent, then that means that these angles have to be congruent because they're both the same type of angle. They're both inscribed angles. So if you think about in terms of the formula, it makes perfect sense. If I were to plug the same number into the same formula, you're going to get out the same angle measure. So again, we have to be specific though. So I'm going to say in a circle, congruent inscribed angles. So you do have to name the angles just like we did for central. So inscribed angles imply congruent arcs. But you can also go the other direction. If you have the congruent arcs, well, then the inscribed angles that cut into those congruent arcs will be congruent. You have to make sure you remember to name the type of angle, because otherwise, if you just said in a circle congruent angles imply congruent arcs, not the case. Central angles and inscribed angles that cut the same arc or congruent arcs will not be congruent to each other. They use a different formula. You've already seen this formula here. Inscribed angles that intercept the same arc are congruent. So I can just kind of shorten this a little, but not too much. So in a circle, inscribed angles that cut, instead of intercept, I usually say cut, that cut the same arc are congruent. So there's really not much I'm shortening that up. I'm just saying cut instead of intercept. But you've seen this. Again, it only works if you're talking about the same type of angle. So if you look at this picture here, angle A is cutting into arc DB, and angle C is cutting into that same arc. So that means since those angles are cutting into the same arc, angles A and C have to be congruent. Same thing is true if I look at it in the other direction. So meaning if I look at angle D is cutting into the same arc as angle B. So those have to be congruent. So right away I know that these two triangles must be similar by angle-angle similarity. This is a very commonly used theorem in circles, so just be aware of that. And again, there's not really a way to shorten this at all. We've talked about this one as well, very common. All radii of the same circle are congruent. We really can't shorten that either. So in this picture, all of these radii are congruent. So keep an eye out for them, look for them. Here's another common one. We've talked about this theorem. An angle inscribed in a semicircle is a right angle. So angle B is a right angle because it's completely contained in half of this circle. You have to have the diameter drawn in order to make this conclusion. So you either have to know you have a diameter or you have to see that it's passing through the center point for it to be a diameter. Then you can make the conclusion that this angle is 90 degrees. So these last three you can't really shorten symbolically in symbolic form, so you're going to really just have to kind of write these ones out. So let's go ahead and see how these are used in proofs. So in this example, they give us arc AB is congruent to arc CD. So these two arcs right here are congruent. So right away, I can go back and look at my circle theorems. And anytime I have congruent arcs, that means I have congruent central angles, I have congruent chords, and I also have congruent inscribed angles. So from there, I can look and see, well, these two chords would have to be congruent. I'm seeing that angle B, or I should say DBC, and angle ACB are cutting into those, so those angles have to be congruent as well. So that's kind of where I could start with this. So let's go ahead and start with that. I have my arc AB is congruent to CD. So that's given. So I can say chord AB must be congruent to chord DC. So this is because in a circle, congruent arcs is what I was given, implies congruent chords. So that's one of our circle theorems. So that basically proves that these two chords are congruent. And then I said, well, what about angle B, or with the vertex at B, and angle ACB? Those both cut into these congruent arcs. So that means since those are both inscribed angles, I'm going to call them angles 1 and 2, those have to be congruent. So I can go ahead and mention that now. I can say angle 1 is congruent to angle 2 because in a circle, if you have congruent arcs, that implies you have congruent inscribed angles. Again, you have to make sure you mention the fact that those angles are inscribed, that they're the same type. So that works. What we're trying to get at here to prove is that angle ABC is congruent to angle DCB. So basically, if I could prove that those two triangles, this blue triangle, is congruent to this yellow triangle, that means I could show by CP/CTC that these two angles are congruent. So that's the way I'm going to go about this. And hopefully you were already thinking that once you saw those congruent angles. So now when I look at the yellow and the blue triangles, we do have the reflexive property right here, the green side. But the issue with using that would mean that we would have an angle side-side situation, which we can't have. We have to have one of our valid congruence methods. So just a refresher on our different methods here. So we have side, 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 angle, 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 side, and HL. So I don't really want to use reflexive because then I'm going to be in the situation of a theorem that doesn't work. So instead, I'm going to think about my circle theorems, and one that comes up a lot is using the diagram. So when I look at the diagram, look at how angle BAC and angle BDC, they cut into that same arc. So these two angles, I'm going to say angle 3 and 4, have to be congruent. This is going to be one of those just kind of floater statements because you can look at it from the diagram. You don't have to be given anything. And we can say that they're congruent because if you have, so in a circle, inscribed, again, you have to say the type of angles, inscribed angles that cut the same arc are congruent. So now when you focus on just the triangles, if you can actually see what's left here, I have angle, angle, side, and then I have angle, angle, side. So I can take these three things, put them together, and say that triangle ABC is congruent to triangle DCB by angle, angle, side, and then by CPCTC, those angles that we wanted are congruent. This is not the only way to do this proof. There's several ways to do this proof. This is just one of them. So with circle proofs, oftentimes there's going to be multiple ways to prove something just because there's so many different theorems that you could have used. So just be aware of that when you're doing this. I'm just looking at this now, and I could have done this without triangle proofs. I could have used angle 1 and angle 2 congruent like I did. I could have then used these small angles right here congruent. By using this inscribed angles that cut the same arc are congruent. And then I could have done angle addition to show that the whole pieces are congruent. So that's a totally different approach to this, not even using congruent triangles. So lots of options here. So let's look at the next one. We start off with some givens, so let's just go ahead and record those so they're done. And I'm going to go ahead and group the perpendicular together because I'll make the same conclusion from the perpendicular. And then I have the midpoint. So lots of different conclusions. All of your old theorems and methods still apply here. So anything that we've done before. Look at where I'm trying to go with this. I'm trying to prove EB is congruent to FB. So hopefully you're thinking, okay, let's prove the triangles that those sides belong to congruent, and then we can use CPCTC to get those corresponding sides. Now the thing is, there's two different triangles that these sides belong to. So if we look at our information that they give us, that'll kind of lead us to which triangles we should use. So I have these two arcs that are congruent, which does mean that these entire chords are congruent, but then that's going to help us prove that the big triangles are congruent, and I don't really need to do that for this. I really want to focus on either these two small ones or triangle AEB and triangle AFB. So I'm not going to use that, but I can use the fact that I have angles. Let me use a different color. I have angle C cuts into that arc, and angle D cuts into this arc over here. So I could say that angle 1 and 2 are congruent using those, which might be helpful because now I'm getting towards those smaller triangles. We also have the perpendicular, which happened to occur, happen to make right angles in those smaller triangles. And if we look at the midpoint, B is the midpoint of CD, that gives us two congruent parts. So really this tells us we should be looking at these two small triangles here, proving that those two triangles are congruent, and that'll give us segment EB and FB are congruent. So what I'm going to do first is from these congruent arcs, I'm going to state that angle 1 is congruent to angle 2. And this is because in a circle, congruent arcs imply congruent inscribed angles. Remember, it has to be the same type of angle, so you have to say inscribed. So that's angles 1 and 2. I have the right angles here. So I'm going to just end up using 3 letters because I don't want to try to squeeze numbers in there. So I'm going to say angle CEB and angle DFB are right angles. So these are just old methods that you've seen before. This is just perpendicular lines imply right angles. And when I look at the method I'll be using, it's going to be angle, angle, side. So since I'll be using angle, angle, side, that means I need to state that these right angles are congruent to get my pair of congruent corresponding angles. So this is true because all right angles are congruent. And then I have the midpoint. So this is just an old method, which gives us CB and DB congruent because midpoints implies 2 congruent segments. So then from here, I have enough to say angle, angle, side. I have all of my 3 pieces, so now I can say that those triangles, CEB and DFB, are congruent by angle, angle, side. Again, here's my angle, angle. Make sure that those are congruent right angles, and side. Make sure you actually say that they're congruent, not just right angles. And then the last thing to say is that those corresponding sides, EB and FB. By CPCTC. So there you have it. It's basically just using your new circle theorems to prove either congruent triangles, congruent parts. You might have to do similar triangles, any other proofs that we've done. It's just adding these new theorems. So since this video went a little bit longer, there is not a section for key ideas or check your understanding problems. We will just continue practice tomorrow in class.